So we learned this actually briefly last class. Okay, so the self-supervision means we can train our network without the tagged data. Okay, so we use some prior knowledge we already had as the supervision signals. Okay, so we can apply the self-supervised learning method on diverse signals like speech, image, video, text. Okay, and so this is one representative example for self-supervised learning. So when training the transformer-based BERT architecture, we actually used the self-supervised learning. So the first task is predicting the masked words. Okay, so given sentences, the sentence data, we can collect this sentence data in the large scale. Okay, and we can mask some of the words in between the words and enforce the network to predict the masked words. Okay, we already have the ground truth for that. Okay, and also the other task is next sentence prediction. Okay, so these two we can know we collected the consecutive sentences as the data. So we already know two sentences are in a sequence or not. Okay, and if the two sentences are in a sequence, we have the label as the is next. Okay, and if two sentences are from distant paragraph, then we will label it as the not next. Okay. 박수근. Okay. This is the self-supervised learning. We can we can generate some labels inherent in the kind of prior in our data set. Okay, that's the self-supervised learning. And in image domain, we already do this kind of self-supervised learning. Okay, so in images, given only images, we can make some labels, okay, using the spatial information. So for these blue patches, we can get some surrounded patches. And for these surrounded patches, we can make some labels. Okay, their relative spatial locations. Okay, and use it as the labels for training the network. Okay, so if this patch is located relatively in this location, their label is 1, and this patches label would be 8 because their relative location to the center patch is right button. Okay, so we predict their relative location labels, and we input the 2 patches here. Okay, so we actually train the feature extraction network and also the final mapping network to predict the relative positions. Okay, and this was proposed in ICCB 2015. Okay, so this is the context called as the context prediction, predict the relative positions of the patches. Okay, okay, and this paper is insisting that rather than predict the relative positions, shuffle the patches and finding their permutations. That is more effective for supervision signals. Okay, so both are self-supervised learning techniques, but this paper is insisting that this type of prior is better for the image classification task. Okay, and also this is the architecture for their method. Okay, So they input 9 patches and find the permutation index. Okay, so this is the kind of permutation and their index. So they regard the permutation, there could be a lot of permutation, and they define the classification labels according to their index, permutation index. Okay. So this is called as jigsaw puzzling. Okay. And another self-supervised signals can be found in predicting the rotations. Actually, even though this is simple compared to previous, but it is this paper, ICLR 2018, they reported that the self-supervised accuracy is better than previous jigsaw puzzling or context prediction. Okay, so this is also good self-supervised signals. Okay. And there were self-supervised signals for videos as well. So inherent in the videos are composed of multiple frames, kind of T frames. Okay, and if we shuffle some of the frames, their temporal index, if we shuffle their temporal index, okay, sorry. This paper is not for that. So given videos, what they try to learn is they extract some patches from the same video. So these two are patches extracted from the same video. These two are extracted from the same video, but in the different frame. Okay, so here maybe. So these two are patches extracted from the same video, but in the different frames. And the other frame, the third frames are extracted from the different video to these two. Okay. And they are saying that the distance between the patches from the same video should be minimized compared to the distance between the frames for the patches extracted from the different videos. Okay, so they propose some of the ranking objective to make the distance between same video patches become minimized compared to the distance between patches from the different videos. Okay, that is called as ranking objective. And this is also some self-supervised signals inherent in the video. Okay. And another interesting signals we can find from the video is the temporal order. Okay, so in the video, let's say this is the correct temporal order of the video. Okay, but we can actually shuffle some of the video, their indexes. Okay, then we can enforce the video recognition network to discriminate the wrong temporal order and the correct temporal order. Okay, that's kind of self-supervised signals inherent in the video. Okay, so here what they do is they have 3 video encoders here. Okay, and these sequence are temporally correct sequence. This is also the temporally correct frames, right? But these are on purpose, we can shuffle some of the temporal index, okay? And then we can apply video clip encoder and also apply some of the FC layers, okay? And then we can classify, we can concatenate their features and classify which is having the old sequence. the strange sequence. So we enforce the video recognition network to find the wrong temporal orders. Okay, this is another self-supervised signals inherent in the video. Okay, also published in 2017. Okay, and also this type of interesting approaches are proposed for the pose estimation task. Okay, so I mean, for the video or image classification, it is rather easy to collect their labels. So for one image, we can collect some image classification labels, maybe within few minutes, maybe within 5 minutes, right? Per image, we can collect it easily. And also for the videos, we can have the labels for describing the content of the video within very small amount of time. Okay, within maybe 1 minute, we can watch the video and can decide which contents, which humans are doing which actions, or which objects are inside the videos. That kind of information we can easily maybe classify and do make some labels for that video within maybe 1 minute. Okay. I mean, relatively for video classification or image classification, getting the labels, it is still hard, but relatively to the pose, the 3D locations of the landmarks, this is easier to collect. Okay, but especially the pose, I already mentioned this in previous lectures. So the labels for pose is some XY or sometimes involving Z coordinate of their bones. Okay, their main joint like this. We have to collect some XY, sometimes Z coordinate of some 20 joint. Okay, this is the pose label. Okay, for one image, collecting this type of labels may take some time. Okay, may take more time than collecting the labels for image classification or video classification tasks. Okay, so anyways, in pose, it is harder to collect the labels. Okay, so but these self-supervised approaches also could be applied to the pose estimation task, and this was kind of the first work that applies self-supervised signals to the pose domain. And what they do is they have two streams, okay, and they require two data, x and x prime. They are describing the same persons, two slightly different pose. Okay, so these two are describing the same person, but they are doing the slightly different pose. Okay, and this network is kind of autoencoder, and it is extracting some features in the middle, and we from that feature we reconstruct the images of slightly different posed person. Okay, I mean the x prime. Given x, it is trained to synthesize the x prime. Okay, but here this vector is composed of two parts. Okay, the purple is denoting the pose vector extracted, and here it is containing some information about the background and also person. Okay, person themselves. Okay, so if we can change the pose vector of this feature with some output extracted from X prime, then this network have to generate X prime. Okay, if this purple is having X pose information, then it would generate X. Okay, but now these arrows are indicating that the pose vectors are some pose pictures are replaced with that of X prime. Okay, and actually in this paper they constitute this pose vector information samely with the same format as the joint coordinate. So there are J number of coordinate and 3 maybe channel. They are having 3 channels for XYZ coordinate. Okay, J is the number of joint and 3 is reserved for XYZ coordinate. Okay, and they are actually using some heat map representation to express the joint location. So this is actually encoding some only the XY. There's no Z here. Okay. Anyways, they extract the joint, but no supervision is applied here because their approach is self-supervised approach. No signal, no supervision is applied here, but they apply this to here, okay? And using this, they synthesize the X prime rather than X, okay? They, if they extract this feature and without replacing with this, then the resultant reconstruction would be similar to X, have to be similar to X, okay? Anyway, without applying some post supervision on this, but replacing this part with this post estimated post and generating some same person's image with slightly different pose, then this will make this close to some joint estimator. Okay, so using this indirect supervision, these networks are trained to be joint estimator. Okay. So the only constraint is we need this same person's slightly different posed images pairs. Okay, using this, we can train both network and the other network become the joint estimator without supplying any pose labels. Okay, so are you guys following this? Okay. So this is the example of the trained pose estimators result. Okay. So one interesting thing is, if there are paired images, the joint obtained could have different topology than we humans are defining. Okay. They are actually, but they are mostly capturing some main joint. The humans are annotating, but that could be slightly different. Okay, and for the face, they also could do similar things and obtain this kind of pose estimate in self-supervised way. Okay, and another interesting approaches are these things published in ECCB 18. Okay, so here the problem is also their motivation is lacking large scale data, pose data. Okay, it is hard to collect compared to the classification data. Okay, so what they did is they did similar things to the previous thing. So but they are having some aligned images, not aligned, mean multi-viewed images for same person, okay? So they have images for this person from the different viewpoint, okay? In this case, they first train some generation network that can generate this image from this image, and maybe generating this image from the other images, okay? They first train this type of unsupervised image generation network. It can be trained using some multi-viewed images only, right? And then they reuse the pre-trained encoder, and they attach some 3D, they attach some shallow neural network on that and train this network to map the intermediate latent vector to the post vector, okay? So the amount of data used for here could be smaller, okay? So their motivation is they don't have large scale post data. Actually, the 3D post data, it is hard to collect. So in the unsupervised way, they pre-train using, they have a lot of multi-view images, okay? So in the unsupervised way, they train this kind of image synthesizer, which would have encoder-decoder network, okay? So this is some image input, and they generate the reconstructed image that could be trained by this encoder-decoder architecture. And they put this encoder only to get some feature vector in the middle, and they train this latent vector to pose network, okay, using some small scale pose data as the supervision signals. So this is the supervised learning, but this is kind of self-supervised large scale training. They do that first and train the later part with the smaller scale data in the supervised manner, okay? So this is also examples for self-supervised learning, okay? And they this is conventional autoencoder, but they have another module to to map certain viewpoint to other certain viewpoint. So they have some modules here to control the viewpoint change, okay? According to this, they predict maybe view 1 image and predict another view 2 images. They learned to reconstruct different viewed images according to this controller, okay? Please refer this paper if you want to know more details, okay? So their architecture, autoencoders are slightly different from the conventional one, okay? Having this controller, okay? Anyways, this is the high level concept for their architectures, okay? And one famous approach is, nowadays many people are doing this contrastive learning because it is powerful, actually. So previous, this kind of image synthesizer or this kind of prior knowledge signals are anyways effective, but it's not that powerful compared to the supervised learning. But this contrastive learning is kind of working very good, even compared to the supervised learning. So many people are doing this actually. So I missed the reference here, but this is the figure from the SIM-CLR paper. So please refer this paper if you are interested in. So what they do is they have same image here, X, and they apply different noises to that image, okay? So generating Xi and Xj, okay? And they apply feature extractor to extract some feature and map it to some output, okay? But this is sometimes, this is also can be thought as the other feature representation. So, and because this X was same, and we apply different noises to that same X, their feature or output should be agreed, okay? They have to be similar, okay? So that is actually written here, but for the non-paired data, I mean, there were X1 and X2 maybe, and if the samples are generated from X2, then these two have to be trained dissimilar. Their features should be trained dissimilar, okay? That's actually written here, okay? So this is the simple concept for the contrastive learning, okay? Contrastive learning, they are making some positive pairs. So these two are positive pairs, and these two are negative pairs, okay? In contrastive learning, we close the similarity between the feature similarity between positive pairs and make the distance between negative pairs, okay? And actually, this N is describing some batch size, okay? So there are 2n number of images in the same batch, okay? Because they apply these two different noises to n batch images, so they generate 2n images, okay? And among 2n images, they apply, they have one positive image, right? But I mean, they apply ij and ji as the different pair. They regard this as the different pair. So there are actually two positive image pairs, okay? ij and ji, which are generated from the same X, okay? And for 2n minus 2 pairs, they regard it as the negative pair, okay? So this, we have actually one, but I mean two positive pair here, but we iterate through 2n numbers, and if their case is not equal to I, they apply the dissimilar rules. So this is the contrastive rules, actually, okay? And they apply this type of different augmentation. So they apply here different augmentation, different noises, and actually make this and this, their features similar, okay? All are positive pairs here because they are from the same image, okay? These are also the positive pairs, okay? But if two noise images are from different image, they are becoming the negative pair and applied here, okay? The bottom of this fraction, okay? And it is interesting to see, this seems clear, their method is even better than the supervised cases in some cases. So, I mean, this contrastive learning is simple, but its performance is comparable to the supervised learning. differently to previous self-supervised signals. So many people are investigating this contrastive learning. Okay. Okay, so this is the summary for the self-supervised learning. So if you think, if you are interested in individual papers, then please search for that, okay? And or even email me for Q&A maybe. Okay. So I just want you to deliver some conceptual things only, okay? And the other topics I want to maybe share with you is the weekly supervised learning. So we learn the self-supervised learning, which requires no supervision, okay? But this weekly supervised learning, it still requires some supervised signals, but it is rather incomplete, okay? That is weak supervised learning. Incomplete supervision we have. So for example, when achieving semantic segmentation, which requires the pixel-wise annotation, but when we are given only bounding boxes or some image level annotations only, we can still achieve this semantic segmentation. There are some approaches proposed for that, and they are called as weekly supervised learning, okay? So originally we need pixel-wise annotation to achieve the semantic segmentation, but we are allowed with, we are given only the incomplete supervision, like the bounding box or image level annotations. In that case, it is called as weekly supervised learning. So I want to share with you the WSOD method. This is called as weekly supervised object detection pipeline. There are several WSOD framework, okay? So they have some target network, which is actually the object detection pipeline. And they have more layers, which is differentiable, but they transfer the object detection output to image classification output in the middle, okay? So target network, their output format is some object detection format, but they add few more differentiable layers on that and map the object detection output to image classification labels. And then they apply image level supervision on that, okay? This is the conceptual block diagram of weekly supervised object detection pipeline, okay? So maybe image, from the image, we first extract some image feature and apply, this is some two-stage object detector we learned, like the faster RCNN. And then they will output the object detection output, but we will actually map it further to the image level. We will actually map it to image level format output and apply the image level supervision, okay? Then through this additional network, this can be further trained using the image level supervision, okay? So this is a kind of frequently used method for weekly supervised approaches, okay? So this is a more detailed diagram for WSOD method. And this is a selective search window or edge box window. You can think this as the object proposal generator. And this is the image input. And this is the, you can think this is some kind of object detector, such as faster RCN. Okay. Their output, we can assume their output is some this dimensional array. Okay, they have multiple bounding boxes whose sizes are. They have rectangles, the multiple bounding boxes outputted from the output of the object detector. They have multiple columns for the bounding boxes, and each bounding boxes, they have probability for C classes. Okay, so we can make this kind of tables. Okay, having some scores for each individual boxes. We have C category probability, but not exactly probability, but the scores. Okay, this is the output of object detector, right? So from the object detector, we may have multiple bounding boxes, and for each bounding box, we have probability or score for C classes. Okay, this is the output of object detector, right? And then we can normalize this array with two directions. So we can normalize it in this manner. Okay, so for each bounding box, we can normalize their scores to make their sum to summing their class probability for each individual boxes. We can make them as one. Okay, we can normalize it like this, like that. Okay, that's actually this part. Okay, so are you following me? 따라오고 있나요? So this is the normalization for each bounding box. Okay, then in this entry, we can get some normalized probability for each class for each individual bounding boxes. Okay, that this is denoting that, and this we normalize in different direction. So we normalize it for this direction. So for each class, we normalize the scores according to their sum. This sum, then their sum in this direction becomes 1. This becomes 1. So this is indicating that for each class probability, for each class, which bounding boxes are mostly having that class. Okay, we can get some scores for that. So if we normalize this array in this direction, then we can get some information about which classes, for this class, which bounding boxes are mostly having that class in it. Okay, we can get such information here. And then, so this is information normalized in this direction. And this is information normalized in this direction. And if we dot producting all the tables, all the arrays of these two array, then the resultant one is having the values whose total sum is 1. Okay. So if we dot product, maybe by normalizing in this direction, we can get same dimensional array, this R by C. And by normalizing it in this direction, we can also have C by R dimensional array. And by dot product element wisely multiplying these two array, by dot producting, we can get the same dimensional array. And in this array, their sum of values would be 1. Okay. And then what we do is doing this. So this is denoting summing these directions. Okay. Then it makes C-dimensional vector. Okay. This is transforming this R by C to C by 1 vector. So for each class, we sum their probability, okay, for bounding boxes. Then what this vector is denoting is image level probability for C number of categories, okay? And then we apply image classification, the cross-central clause to this vector have the image classification probability. So, I mean, for this image, we know that there are horse and human, right? Okay, we can have some one hard encoded ground truth for this, right? And actually, we can train this C is denoting the number of classes in the image. So this additional module is mapping the object detection output to the image classification format in the differentiable way, okay? So anyway, via this, we can get image level probability, and that is supervised by the image level supervision, okay? So via this differentiable module, the earlier part also could be trained, okay? So this is the concept of weakly supervised object detection. And this is the result, okay? So are you guys following this? Okay. And this is another work published in ICML 18 and kind of old work, but this is, I mean, efficient to understand what is WS as semantic segmentation, weakly supervised semantic segmentation. Okay. So this is the original image, and from the image, we extract some patches with this size. These small sized patches we first extract. And what we do is we have the labels for this original image. We only have the image level annotations. Maybe this image is denoting some digits. So seeing this image, we want to classify this image is having some digits or not, okay? So we don't have any segmentation labels for this image, okay? But we are processing this image classification by first extracting this type of small patches, okay? And then, from these small patches, we extract some attention value, which has a value from 0 to 1, okay? So from each patch, we actually extract two things, the feature vector H and the attention value A, okay? And then by this formula, which is differentiable formula, we extract the global feature for whole image, by multiplying the attention and each patch's feature. Okay. So there are K patches here, K patches. For entire K patches, we extract their weight A and their feature H. And then we sum them to make the global feature for whole image. This is differentiable operation, right? And then we map it to image label. Okay, this is here we need more F's layer, right? Then actually what we can obtain is this A. This is weight for each patch, and if we visualize it, we can have this kind of visualization. So AI is meaning the weight for each patch, how much each patch is contributing to classify that image into this label. Okay, so it means without the segmentation label like this, so these patches are denoting that in this part there are some disease. This is some ground truth for pixel-wise ground truth for the disease. But even without this thing, using only the image level annotation, but by constituting the network like this, we can get the weight for each patch, okay? And if we visualize it, this coincides with the segmentation label, okay? So this is one way to achieve the weakly supervised semantic segmentation, okay? The segmentation, we do not use any segmentation label in the middle, but train the network using only image level supervision here, disease or not, okay? But we constitute each patches to estimate their weight and feature, and summing their feature with weight, get the global feature, and have the F layer to map it to the global image level supervision. And this way, we can obtain the weight estimator for each patch. And that can be actually the module for achieving the segmentation, okay? So are you guys following this? Okay. And another popular method, which is helpful for achieving the semantic segmentation, weakly supervised semantic segmentation, is CAN. Okay. So many people are nowadays using this CAN to achieving this WSSS. Okay. So what this CAN is doing is, maybe you can refer this paper for details about the CAN. What CAN is doing is, you will train the entire network as the image classifier, but in the middle, you can get this kind of attention map. Okay, so if the image, their classes are face, then in the middle of the network, some parts are attend to the face regions. Okay, so this is similar to the aim of the WSSS. So people are using this CAN for this task. Okay, so but for training CAN, the last part have to be slightly changed. Okay, so in the middle of the network, we have kind of 2D activation map, which is the FK x, comma y. So this is denoting A, and K is index for each channel, and there are actually n channels. So this is a 2D map, middle of the network, and this is global average pooling to make the 2D signal to the one-dimensional scalar value, okay? So because there are n map, n 2D map, there are n scalar value appear here, okay? And then by making some probability by multiplying some weight to this n scalar value, you will get the probability for each category, okay? That is actually called, formulated like this. So SC is denoting each C's class score. SC is the score for the C's class, okay? So that could be formulated like this. Okay. And actually, if we, so from this activation map, we can exchange their orders slightly. So we can directly multiply the WK to FK. Sorry. And then we can sum them to map it to each C classes activation. So this is called as CAM. Okay. So the final result was 1D probability before, but by slightly changing the order here, you can remain the last part as the 2D map. And that 2D map is actually localizing the object location, okay? That is done in CAM. So this MC is the 2D response map denoting the C's class object locations, okay? So you can get this type of map via CAM, okay? And if you apply some smoothing method for the CAM, then you can get this type of refined masks. So this is popular method. So this is some noise input, and if you apply the method proposed here, then you can get some refined denoised result. Okay, so there are already some techniques like that. So some people do refine this CAM, which is coarse representation, right? But considering the pixel values here and nearby probability, you can actually refine it using, this is the example for that. And this is also some explanation about that. And then you can get this refined segmentation mask, okay? This is the CAM, but there are some limitation in CAM, which is CAM cover most discriminative part of an object, which means when humans are in the image, CAM activate like this, right? In this part, there are human, right? But the activated part, this is most discriminative part of human, okay? So CAM always means non-discriminative part like the foot or hand or the faces like that. So this is the limitation of the CAM. It can miss some of the non-discriminative part, okay? So not the entire object. The CAM only capture the most discriminative part, okay? So this paper, what they do is very simple. So they first get some attention map, maybe using CAM, and they threshold it to make some drum mask, okay? And this is the original, the importance map. So the activated region is encoding the importance, okay? Similar to CAN, this kind of map is denoting which part is important, right? But on purpose, they have another stream here, and they make drum mask, okay? They threshold and find the most activated region and make the drum mask, and actually delete that most activated part on purpose during the training. So here, they actually delete the most activated part and make the new attention map and multiply it to the feature map and do training. Then they are saying that the most discriminative part are removed from the attention, and the next discriminative part are gradually trained. Okay, that's the motivation of this paper. But they say if they do that every time, then they can lose some performance. So they do it randomly during the training. Okay. So they say they can improve the training. Okay. So this is the CAM result. Only the this part are activated, not capturing entire object, but using this ADL scheme, they can get they can tend to capture the entire object. Again here, only this part are highlighted, but using that kind of drop mask thing, they can get the entire object. Similar here, right? Okay, so this is simple idea to improve the CAN. Okay, and this is the last slide. Okay, so this is rather a recent paper, and for the WSS. Okay, what they do is, I will explain this in the conceptual level maybe. So they are having B number of images in the same batch during the training, right? And they extract C channeled and which have 2D dimensional back array. So this is the feature dimensions, right? C by H by W, this is the feature dimension, and there are B number of that, which is extracted from the B number of images, okay? And there could be multiple classes, okay? So maybe this is a COCO data set and having multiple classes within it, okay? And for example, this image, human is here and motorbikes are here, right? So this feature is denoting the activation, encoding some self-attention, okay? Person location and motorbike location, okay? And this second image, person is here and horse is activated here. And here, horse is in the middle, right? So we actually, anyways, extract the B number of feature map, which encodes the spatial location for each cis object, okay? And then we use this as one input to the subsequent layers, and this as the one input, and this as one input. So this is indicating that the same object, their feature map appeared in different images, okay? So they actually use this as the input during the training for the further process, okay? And then they, this is denoting these three, okay? This is denoting these three. And they actually get the self-attention from these multiple images, same object response map. From this, they get self-attention map and map it to classifiers, again, for individual images, okay? So this is denoting that. So there are B images feature map here, okay? And for this is the feature map, concatenated feature map for B images for case class, okay? So this FK is having all the feature map for that class from multiple images, okay? So this is having feature maps extracted from multiple images for case class, okay? And we get the self-attention from that feature maps, okay? And by inputting this attention, we make it into one scalar, 2D response as the one scalar, but having some multiple dimension, and map it to the some label, okay? And we train this output to be same as the label, okay? This is the way they train. So, I mean, because in this WSSS, they don't have pixel-wise ground truth. So by comparing with images in the same batch, they somehow extract some ground truth images, right? So maybe I mean, so from the same batch, if they have the same object inside, they will be activated, okay? I mean, anyways, considering those kind of co-activation, they map it to the some kind of, they map it to the label information, and using that, they train the, I mean, this part, and also they flow the gradient from here to the earlier part and train the, I mean, network. Okay. So this is technique, anyways, used here. Okay. So maybe I will continue again for this part in next class, maybe. Anyway, this was the summary for the self-supervised and weakly supervised method, and it can be a way to prevent collecting the large-scale data. Okay, so this is the summary, and we learned about several techniques for achieving WSOD and WSSS. Okay, and also learned about the self-supervised techniques. Okay, so let's finish here for today's class. Okay, and see you guys next week, and we will